Welcome back to the channel. In this video, we're going to expand upon the previous video where we set up the static outgoing IP for the Lambda function all manually. In this video, we're going to do it all with Cloudformation. So we're going to automate it to make our lives a lot easier, not only to create the components, but also to delete the components. Before we jump into the code, let's remind ourselves of the diagram. We have the NAT gateway. Behind the NAT gateway, we have the Lambda function. The Lambda function sends us request to the NAT gateway, which routes that request to the internet gateway, which finally sends it to the internet. And then we reverse that same path to return the request. The more complex diagram is here. We have the AWS Cloud in the top left. This encompasses all of our components: the internet gateway, the router, the NAT gateway, the Lambda function, the subnets, and the route tables. We have the internet gateway sitting outside the VPC because the internet gateway is what actually talks to the internet. Inside the VPC, we have the NAT gateway sitting in the public subnet. This is what routes requests to the internet gateway. And that's where we assign the elastic IP, which is the static IP address, to our requests. In the private subnet, private means not accessible from outside the internet, we have the Lambda function. This is where the request originated from. And with the NAT gateway, no request can come into it. Requests can only be made from out of it and then return the appropriate response. And outside the AWS box that's still contained in AWS is the route tables. We have the route table for the NAT gateway. We're saying send all traffic to the internet gateway that is outside the private subnet assigned to the NAT gateway. And at the main route table, we're saying send all the traffic outside the private subnet and send it to the NAT gateway. Before we jump into the code, you can help me out a lot by doing a few simple things. You can support me on either Patreon or GitHub sponsors, subscribing to the channel, liking this video and sharing it on platforms you use like Reddit, Discord, etc. Starting the repo on GitHub, and also follow me on GitHub. All these things help me out a lot, and I'd really appreciate it. So let's jump into the code now. All right, so this is the repo we're going to be working with. You can go and clone the repo by going to code, click clone, go to your terminal, and just do git clone and paste the URL. Once you're in there, go and open up the code in your favorite code editor. I'm going to be using Visual Studio Code. So let's start walking through the code. The first file we're going to walk through is the VPC Cloudformation.yaml. This is the file we're going to use to create all the components on AWS. What this template is doing is creating a few different components. It's creating the VPC, the virtual private cloud. It's creating the subnets, one public, two private, the route tables, the internet gateway, and finally the NAT gateway. It's creating all these components automatically for us, so we don't have to go in and create these manually and worry about any kind of subnet associations and linking all these components together. We're going to specify it all here. One thing that's different with this template compared to the previous video is we're creating two separate route tables in addition to the ones we created in the previous video for the private subnets. Each private subnet is going to get its own route table. The reason is, in the previous video, for the main route table, we set all traffic to go to the NAT gateway. This was very easy, but unfortunately, in Cloudformation, we cannot modify the main route table. So we have to create individual route tables for each private subnet to route the traffic in those private subnets to the NAT gateway. We'll see that in action as we go through the script. So to start off, we have parameters at the top. These aren't actually creating the resources. This is where we specify different parameters we want to use in the creation of the resources. The first is just the environment name. This is what we're going to use as the prefix for all of our components. In the previous video, we were using AWS Lambda static IP demo. We're going to keep that convention here. The CIDR, we're specifying the CIDR for the VPC. We're doing top level domain and 16. This is the lowest you can go. This gives us the maximum amount of allowable IP addresses. If you want to understand why I'm using these values specifically, you can refer to the previous video where I go into it in more depth. The public subnet, we have 10, and the privates, we have 20 and 21. No overlap between the public and the private subnets. This is by design and must be done. So we specify the different parameters. Then we can move on to the resources. The first thing we're creating is the VPC. You see here, representing the VPC CIDR, which is up here. We're using the same name. This is how you reference. You copy the exact same name you chose, and then you can reference it here. So we're specifying the CIDR block for the VPC from the parameter that we passed in. And then we're giving the name, the environment name, which we specify up here, and we're just appending VPC with a dash in between. Then we create the internet gateway, again, referencing the environment name from before and IGW. Then we attach the internet gateway to the VPC right here. We create the first public subnet, and we're specifying the availability zone as US East 1. If you're in a different availability zone, you can change that here to US West 1 or whatever you want. And we're referencing the public subnet 1 CIDR from our parameters at the top. And we also specify the name. Then we're creating the private subnet 1, US East 1, select 0, because there's 6 options for each availability zone, A, B, C, etc. And private subnet 2, we specify a 1 here, because we cannot have the same selection of availability zones for each private subnet. It must be different. Even though they're both US East 1, this will be US East 1A, and this will be US East 1B, so there's not direct overlap. And again, the naming as well. Keep going. NAT Gateway 1 Elastic IP. Elastic IP is the static IP address we're going to assign to the NAT Gateway, which is going to assign that static IP address to the request from the Lambda function. In this video, though, we're only creating one NAT Gateway. We have this second one down here because this template that I'm pulling from right now comes directly from AWS. Right here, I'm just copying and pasting this, but I made a few modifications. You can refer to this template if you want direct from Amazon, and I'll also link it in the description. But here, we're not using a second public subnet, and so we don't need a second NAT gateway. That's why you see some of this code commented out. So we create the Internet Gateway attachment. Scrolling down, we create the NAT gateway, referencing the public subnet 1, and we're giving it the name NGW. Great. Public route table, referencing the VPC. Default public route, Internet Gateway attachment depends on. This means that the Internet Gateway attachment, which we have up here, must be created before this component can be created. It forces consistency in which components are created in order. This saves us a lot of trouble because if we're manually creating components, we can forget that we need to create a component before we create another component. Even more so when we're deleting components, it makes our lives a lot easier because the script will automatically know which components to delete before the other ones. So we have to worry about all these dependency issues, trying to delete a resource and Amazon saying, you can't do this, there's still dependencies. It's going to take care of all that for us. And the route table ID, public route table, the one we just created, and saying send all internet traffic to the internet gateway we created, which is exactly what we did in the previous video. And we associate the public subnet with the public route table. Great. And like I said before, we're not doing a second public subnet. This is commented out. You can add this back in if you want and rework the code. Now we're working on the private route table. This is where it's different from the previous video. Previous video, we modified the main route table for the NAT gateway that's automatically created when you create the NAT gateway. However, we can't modify the main route table. So you have to create separate private route tables for each private subnet. That's what we're doing here. Again, private routes, we're just giving it a name. All traffic to the NAT gateway. Subnet association, private route table 1, we're associating with private subnet 1. And we're doing the same thing here, just for the second private subnet. And finally, we have a few outputs. These aren't very relevant to the video. They're just going to show up at the end of the creation of the CloudFormation script. They just come from the default template script that I showed you on Amazon. You don't have to be too concerned with these, and you can ignore them. Let's also step through the other files, just to remind ourselves again. We have the app.py. All it's doing is just calling this one URL and returning the response. This URL just returns whatever IP you're using to connect, which is perfect to test the static outgoing IP of our Lambda function. Docker file, we're using Python as a base image. We're copying app.py requirements.txt, which just has requests, because that's our only import. It's installing the requirements and calling app.handler, where app refers to app.py, and handler refers to the function handler that takes an event and context argument. Great, so that's the Docker file, the app.py file, and the VPC Cloudformation.yaml file. Now let's transition over to AWS and actually run the CloudFormation stack. So run the management console. We're going to search for CloudFormation. Click into it. Create stack. We're going to upload a template file and upload your template file, the VPC CloudFormation that we were just working on. Click next. Enter a stack name and keep the same prefix. And just call it stack. Environment name, same as before. We're going to see this as a prefix for all of our components once they're done creating. The CIDR for the private, public, and VPC are all specified here as default template values. You can change these though if you want. You can make this 193, 193 if you want. We're going to leave it as 192 for now. We can absolutely change these. These are just default values given to you. Click next. You don't need to do anything here. And next. And create a stack. Great. I'm going to fast forward to once the stack is done creating. Okay, the stack is done creating. So now we can actually verify the components are created. Go to AWS, open up a new tab. Let's go to VPC. Now start walking through the components. Go to your VPCs first. Here we go. AWS Lambda static IP demo dash VPC. And we see our CIDR that we specified. Go to subnets. Here's all of our subnets. Great. Route tables. Here's the big difference. With the VPC route table, we have the public and private route tables. These two private route tables, we did not have these in the previous video because we didn't need to. We had this main route table up here. We can just modify this here right now, give it a name so we know what we're doing. We modified this main route table in the previous video. We went to routes, we edited routes, we did 0.0, and we sent it to the NAT gateway. That was easy, right? We can't do that in CloudFormation because we cannot modify the main route table in CloudFormation. That's why instead, we created these two private route tables. Reach route, we're saying that all traffic to the NAT gateway and the subnet associations is with each one has one private subnet associated with it. So this was the workaround with CloudFormation. Yes, we have two route tables more than we would have if we had done it manually, but it saves us a lot of time because it's all automated. So it's much more preferable. You go to the internet gateway, we see that here, IGW, and we go to NAT gateway. Right here. Perfect. We can also scroll down and we'll see the elastic IP address right here. This is what we're going to check in the Lambda function to make sure we have the elastic IP address assigned. So let's open up a new tab and create the Lambda function. Before we create that though, we got to go to ECR, Elastic Container Registry, and push our Docker image so we can actually point our Lambda function to the ECR repository to run it. So let's go to ECR, get started, do private because we don't want it accessible on the internet. Paste the prefix and ECR. Great. Create repository. Click into it. View push commands. We're just going to copy and paste each one of these. Before you're able to run these, make sure you have Docker Desktop running on your machine. And also, if you don't have AWS Management Console installed on your local machine, you have to do that as well and run AWS configure to set the user. If you're not familiar with this, you can refer to my previous video series on AWS Lambda to see exactly how to do this. So we go here, paste the first command, log in. Great. Go back. Docker build, paste. Docker tag, paste. And Docker push, paste. All right, once it's done pushing, we can go back, close this, refresh. Great, we see the image. Do another tab. Now let's create the Lambda function. Create function, container image, same prefix, let's call it Lambda, ECR, and latest. Select image, great, create function. Okay, the function is created, close this, scroll down, go to tests, and test. 18234, is this our static IP? No, it's not, because we haven't assigned the Lambda function into the VPC yet, so it's not going to use the static IP. So first we have to change that. Let's go back, configuration. Just like before, we can't automatically do this. We need to add the permission to the role to be able to do this. So we go to permissions. Here's our role. Let's click into it. We need to add a permission here. Do add permissions, attach policies, do AWS Lambda VPC access execution role, attach policies, policy was attached. Great, go back. Now we can go to VPC, click edit, and use the one we created with CloudFormation. Subnets, we're going to select both the private subnets, private subnet 2, private subnet 1. And security group, we're just going to use the default. Save. Okay, once the function is done updating, you can close this, scroll down, go to test, test again. 5019, 5019. Great, the function is working just as we wanted. All right, so that's how we do it with CloudFormation. The last step is to delete all the components. If you watched the previous video, you know how much of a time-consuming process and how annoying it is to delete the components because you have to be done in a certain order to make sure there's no dependencies. You can't just delete the VPC automatically. You have to delete all the components assigned with the VPC before we can delete it. We're going to show how easy that is with CloudFormation. Before we do that though, you need to go to Configuration and make sure you remove the VPC here. Click Save. Once that's done, you can go to Functions. Let's go and delete the Lambda function. Type delete. Great, that's deleted. You go to ECR. Delete the repository. And then we can move on to the CloudFormation and just click delete. Before you click this though, make sure you give around 30 seconds or so after you remove the VPC from the Lambda function. Otherwise, AWS has problems deleting all the components and sometimes hangs. It must be a lingering dependency with VPC. I couldn't get a straight answer. So just recommended wait about 30 seconds, then click this delete stack. Once you've given about 30 seconds or so, you can click delete stack and watch it in progress. I'll go ahead and fast forward once it's done deleting. Great, once it's done, you won't see the stack up here anymore. You can scroll down, see all the components deleted. And that's just how easy it is. It takes care of itself all automatically, makes our lives incredibly easy, and saves us all the painstaking time of deleting each component and worrying about dependencies. That's it for this video. If you have any questions, just leave a comment below and I'll respond as quick as I can. Thanks for watching and stay tuned for more.